For the biaxial bending worked example, we're given this information, so it's a beam section, and I'll come on to what the numbers mean in just a second, but it means it's effectively an I section. And we're asked to calculate the normal stress distribution, so obviously bending moments will give rise to a normal stress distribution at mid-span if the section is used as a 5 metre long simply supported beam. And we're given two distributed loads, so one of 2.5 kilonewtons per metre acting downwards in the negative x2 direction, so this will be important when we come to orientate ourselves, and one distributed load of 1 kilonewtons per metre acting on the left hand side of the beam in the positive x1 direction. So again, I'll come on just in a second to what we mean by the negative x2 direction and the positive x1 direction. We're given a similar set of assumptions to those that we've used in the previous worked example, so I won't go into those any further. We're asked, again, just to think about our answers from part A as part of part B. So we should state whether any part of the beam is likely to yield under the loading. So obviously that's making sure that the stresses are below the yield stress of 355 megapascals. And then finally, we're just asked to use our simplified calculations approach to check the values again of the area and the second moments of area about the x1 and the x2 axis as they're given in the section tables. Okay, so we refer to I sections in the same way that we refer to H sections. So the first figure is essentially the overall depth of the section in millimetres. The second figure is the breadth or the width of the section, also in millimetres. And then finally, the third figure is the weight in kilograms per metre. And the way that we use I sections, I've drawn on here. So x1 is going to be our major bending axis. So I11 is equivalent to I max because we're dealing with a symmetric section. And then x2 is obviously our minor bending axis going up and down here. I've not drawn it quite spot on. It should obviously go straight up and down the web like so. And obviously x2 is associated with the second moment of area I22, which in this case will also be the minimum second moment of area. So if we imagine that we've taken a cut through our simply supported beam, so effectively the x3 axis is coming out of the page towards us like so, so just coming straight up in this direction, then the loading that we've been told about, so we have a distributed load that's going to be acting down the way in the x2 direction, and we also have a distributed load that said it's acting on the left hand side of the beam in the positive x1 direction, so that's going to be coming across and acting in this direction like so. So for the solution, what I'm doing is I'm writing out first of all obviously the information I have. So I've taken the information on the area and the second moments of area from the section tables for the section that we're looking at. I've drawn out the setup for the simply supported beam, so obviously we have our 5 metre length here, and simply supported just means that we're not trying to restrict any of the rotational degrees of freedom, so we'll essentially in this case have two vertical supports. Because the beam is uniformly loaded, I actually know also that RA and RB are going to be equal to each other, and what I've drawn here is the axis system showing the positive convention that we've previously developed for M1. So you can see X2 is the vertical axis going here, X3 is the horizontal axis going across here, and then actually X1 would be the axis going into the page like so. So on the diagram over here, I've shown my conventions again for what I treat as positive at the cut. So V2 would be the shear force in the X2 direction, and I'm going to take the positive convention of that going up the way. And then M1, based on our positive convention for M1, so remembering the right-hand screw rule, if I was to line up my thumb going into the page like so, and then rotate, you can see that actually this means in this particular plane, as we look at it, that a positive moment will be going in the clockwise direction like so. So having said our conventions, everything else is pretty straightforward from there. So we've already agreed that RA is equal to RB, and both of them will be equal to WL over 2. So obviously W is the distributed load, L is the length, and we're dividing by 2 because obviously the load is split between the two supports. This gives us the shear force diagram here, and then we will also be able to develop the bending moment diagram, and we can either obviously do that based on using the convention of taking the moments at the cut, or we could, based on the conventions we've used, simply integrate the shear force diagram to give us the bending moment diagram. So we've got a way of confirming the result there. Now we can see from the bending moment diagram, and also if we just think about what the loading is doing, then the loading is actually going to produce tension in the bottom of the beam. So the convention that I've got for bending moment is to draw it on the tension side, and that's what the particular conventions that I've set out are consistent with. So if we have tension in the bottom of the beam, then this tells us that in this case, M1 must be negative. So dealing with the bending moment M2 is the same approach as we were using for M1, but we're just imagining that we're looking at the beam in a different plane. So the plane that I'm now looking at the beam in is we have X1 going in the upwards direction here. We still have X3 going in the horizontal direction over here. And then I've drawn X2 based obviously on the Cartesian convention, so based on a right-handed axis system. And I've drawn the positive convention for M2 here. So what that leaves us with is, at the cut, we effectively have the same set of conventions for the shear force. So obviously V1 this time is the shear force in the X1 direction, and M2 is the bending moment about the X2 axis. But because we have the positive convention that we're actually pointing the double-headed moment arrow in the negative X2 direction, when we look in the X1, X3 plane, this leads to a very similar convention to what we were using for M1. So obviously what I'm doing again is, in this case, M2, the double-headed arrow, would be pointing directly into the page, and so I've taken my thumb, lined it up with that direction, and now I'm obviously twisting like so. So we end up with this clockwise will be the positive moment when we're looking in the plane from this particular location. So the loading, because it was going in the positive X1 direction, I've actually shown on the underside of the beam as if it's obviously pushing in this direction. I've shown RA and RB in the positive convention, and obviously when we go on to calculate them, what we'll find is that actually they come out as a negative value, which simply indicates that they're acting in this direction, like so. The shear force diagram we can produce very easily by calculating obviously the shear force at the cut as we move the cut along from this side of the beam to the right hand side of the beam, and then similarly we can either calculate the bending moment at the cut, or we can integrate the shear force diagram, and that'll give us this bending moment diagram. So again, there's a way of checking your calculations going between the shear force diagram and the bending moment diagram. And then finally, so this bending moment diagram, but also if we just think about physically what's going on, then we can see that we're going to end up with tension on the right hand side of the beam. And the convention that we developed before is if there's tension in the right hand side of the beam, then our M2 value is going to be positive. So what I'm doing in this diagram here is we're going to make some assumptions. So when we draw the stress distribution, we're going to draw it as if we're using, or as if we're finding it along the center lines of the different parts of the cross section. So that means that we're interested in finding it along the center line of the flanges here and here, and then also just coming down the center line of the web there. So what that means is that I've just taken the dimensions from the section tables and I've worked out the centerline distance between the two flanges here, and obviously we know that the centerline of the web is just going to be along the X2 axis. So to find the stress distribution, because we're dealing with a symmetric section in the I section, that means that we can use the simple biaxial bending formula. And you can see that in this we have M1 and M2, and I11 and I22. So effectively, we're just ending up with a constant times the x2 position and a constant times the x1 position, all compared to the centroid of the cross-section. So I've just carried out the calculation here. What I'm doing is I'm converting all of the units into newtons and millimetres. So that's why for the moments we're multiplying by 10 to the 6. And for the second moments of area, as we've got them from the section tables, I just obviously have to multiply by 10 to the 4 to convert from centimetres to the 4 to millimetres to the 4. And then we end up with this equation here. So as we agreed, we have a constant times x1, and in this case we actually end up with a minus a constant times x2. Because we have a constant times x1 and a constant times x2, what we know is that the stress distribution is just going to vary linearly from one point to another. And so what I've done in order to plot the stress distribution for the particular cross-section and the particular loading setup that we have is I've just put in the values that I'm interested in, so in terms of x1 and x2. I've obviously used the formula that we found and just calculated the stress value here. So that's all that this table is doing. This diagram here is then the combined stress distribution due to M1 and M2. So I've just indicated compression areas using blue and tension areas using red. What I've done on the side here is I've just plotted the diagrams if we were only looking at M1 and M2, and this is really just to confirm that the complete diagram is effectively a summation of these two diagrams. So because we're in the elastic regime, we're using the principle of superposition. An important point just to note for these diagrams is that they're obviously not giving an indication of the direction of stress. The stress in all of them is coming out of the page directly towards you. So when we have a tensile region, it's coming out of the page towards you like so. When we have a compressive region, on the other hand, it's as if it's going back into the page like so. For part B of the question, I've concluded that I don't expect the beam to yield at any point under the loading. And the reason for this is we've looked at the magnitudes of the stresses at midspan, which is going to be the worst case scenario for this particular type of loading on a simply supported beam. And none of the stress values were anywhere near the yield stress value that we've got of 355 megapascals for a grade 355 steel. So for the final part of the question, I'm obviously referring back to the diagram that I've already developed. So this is the simplified geometry of the cross-section. So for the area, it's simply a matter of having the two flanges, so that's these terms in here, plus the area of the web, so obviously that's the calculation going on here, and we end up with a value that's just 1% different compared to the value in the section tables. For I11, so that's the bending moment, or rather the second moment of area about the x1 axis, we just go through the same process as we've been through before when we looked at the previous worked example. So we have the local contributions from the parallel axis formula. So the local contributions, obviously here we have the contribution from the web part. Here we have the contribution from both of the flanges, so the top and the bottom flanges here and here. And then obviously we have the area contribution, so the area contribution from the flanges in here, and obviously we don't have a web contribution because the centre of the area of the web is the same as the overall centroid for the cross-section. And we end up with a value just 2% lower than the value quoted in the section tables. Finally, calculating the I22 value, so this is obviously the second moment of area about the x2 axis here. So we have the contributions from the flanges in this term, the contribution from the web in this term, and again, because the areas of each of the individual rectangles that I've got here are coincident along the x2 axis with the centroids, that is the x1 bar value is equal to 0. We don't have any additional contributions, and in this case, when we round, we actually find the identical value to that listed in the section tables.